Okay, hi everyone, welcome back to this video series on the Comptia Security Plus course, Honeypots and Honeynets. Honeypots and honeynets attract and trap potential hackers to counteract any attempts at unauthorized access of the network. This isolates the potential hacker in a monitored area that contains dummy resources that look to be of value to the perpetrator. While an attacker is trapped in one of these, their methods can be studied and analysed, and the result of those analyses can be applied to the general security of the functional network. A honeypot is generally a single computer, but could also be a file, group of files, or an area of unused IP address space, whereas a honeynet is one of more computers, servers, or an area of a network. A honeynet is used when a single honeypot is not sufficient. Either way, the individual computer or group of servers will usually not house any important company information. Various analysis tools are implemented to study the attacker. These tools, along with a centralized group of honeypots or honeynet, are known collectively as a honey farm. One example of a honeypot is the spam honeypot. Spam email is one of the worst banes known to a network administrator. A spam honeypot can lure spammers in, enabling the network administrators to study the spammers' techniques and habits, thus allowing the network admins to better protect their email servers, SMTP relays, SMTP proxies, and so on. Over the long term, it might ultimately keep the spammers away from the real email address because the spammers are occupied elsewhere. Some of the information gained by studying spammers is often shared with other network admins or organizations and websites dedicated to reducing spam. A spam honeypot could be as simple as one single email address, or as complex as an entire email domain with multiple SMTP servers. Of course, as with any technology that studies attackers, honeypots also bear risks to the legitimate network. The honeypot or honeynet should be carefully firewalled off from the legitimate network to ensure that the attacker can't break through. Often honeypots and honeynets are used as part of a more complex solution known as network intrusion detection system, discussed following a short review of data loss prevention (DLP). Data loss prevention (DLP) systems are designed to protect data by way of content inspection. They are meant to stop the leakage of confidential data, often concentrating on communication. As a result, they are often referred to as data leak prevention (DLP) devices, information leak prevention (ILP) devices, and extrusion prevention systems. Regardless, they are intended to be used to keep data from leaking past a computer system or network and into unwanted hands. In network-based DLP systems deal with data in motion and are usually located on the perimeter of the network. If data is classified in an organization's policy as confidential and not to be read by outsiders, the DLP system detects it and prevents it from leaving the network. Network-based DLP systems can be hardware-based or software-based. An example of a network-based DLP system would be one that detects and prevents the transfer of confidential email information outside the network. Organizations such as Checkpoint offer DLP solution, and there are some free open source applications as well. Going further, there are cloud-based DLP solutions available, but it all depends on where you store your data. If you store some or all of your data on the cloud, or if you have a large bring your own device BYOD or choose your own device CY of depopulation, then cloud-based DLP becomes an important part of your security strategy. Because the data and the security of the data is now external from the company, planning becomes even more vital. Some key elements of the security mindset include: 1. Planning for the mitigation of security risks. 2. Adequate understanding of the cloud provider, where and how data is stored and their service level agreement (SLA). 3. In-depth analysis of code and the types of data that will be stored in the cloud. And 4. Strong authentication, auditing and logging. If all this is planned for and implemented properly, it can build the organization's confidence in the cloud, which can lead to a smoother transition, and ultimately reduce risk. As for DLP, the monitoring of possible leaked information could become a privacy concern. Before implementing a system of this nature, it is important to review your organization's privacy policies. Leaks can still occur due to poor implementation of DLP systems, so it is essential to plan what type of DLP solution your organization needs, exactly how it will be installed, and how it will be monitored. NIDS versus NIPS. It's not a battle royale, but you should be able to differentiate between a network intrusion detection system (NIDS) and a network intrusion prevention systems and NIPS for the exam. Although a great many attacks can hamper an individual computer, just as many network attacks could possibly take down a server, switch or router, or even entire network. Network-based IDSs were developed to detect these malicious network attacks, and network-based IPSs were developed in an attempt to prevent them. A network intrusion prevention system (NIDS) by definition is a type of IDS that attempts to detect malicious network activities, for example port scans and DOS attacks, by constantly monitoring network traffic. It can also be instrumental in rogue machine detection, including rogue desktops, laptops and mobile devices, as well as rogue access points, DHCP servers and network sniffers. Example of NIDS solutions include open source products such as Snort, https www.snort.org, Bro, https www.bro.org, and many other commercial hardware and software based products. A NIDS should be situated at the entrance or gateway of your network. It is not a firewall, but should be used with a firewall. Because the NIDS inspects every packet that traverses your network, it needs to be fast, basically to slow the NIDS, to slow the network. So the solution itself, computer device it is installed on and the network connects of that computer device all need to be planned out accordingly to ensure that the NIDS does not cause network performance degradation. Figure 8.5 illustrates how a NIDS might be implemented on a network. Often it is placed in front of a firewall. The NIDS detects attacks and anomalies and alerts the administrator if they occur, whereas the firewall does its best to prevent those attacks from entering the network. However, a NIDS could be placed behind a firewall, or you might have multiple NIDS points strategically placed around the network. If the NIDS is placed in front of the firewall, it generates a lot more administrator alerts, but these can usually be whittled down within the firmware or software of the device running the NIDS, regardless of where the NIDS is located. A network administrator should monitor traffic from time to time. To do so, the computer, server or appliance that the NIDS installed should have a network adapter configured to work in promiscuous mode. This passes all traffic to the CPU, not just the frames addressed to it. Figure 8.5 illustration of a NIDS placement on the network. So here you have the Internet Network Intrusion Detection System, firewall and the switch. The beauty of a NIDS is that you might get away with one or two NID points on the network and do away with some or all the NIDS installed on individual computers, effectively lowering the bottom line while still doing a decent job of mitigating risk. A couple of disadvantages of NIDS, aside from possible network performance issues, are that it might not be able to read encrypted packets of information and will not detect problems that occur on an individual computer. Therefore, to secure a network and its hosts, many organizations implement a mixture of NIDS and HIDS. If a NIDS is placed in front of the firewall, it is subject to attack. Therefore, it should be monitored and updated regularly. Some NIDS solutions will auto update. Finally, the biggest disadvantage of a NIDS is that it is passive, meaning it only detects attacks. To protect against and prevent these attacks, you need something active. You need a NIPS, a network intrusion prevention system. NIPS is designed to inspect traffic and, based on its configuration or security policy, either remove, detain, or redirect malicious traffic that it becomes aware of. The NIPS, as well as the NIDS, is considered to be an application aware device, meaning it can define different types of packets, define what application they are based on, and ultimately permit or disallow that traffic on the network. More and more companies are offering NIPS solutions in addition to or instead of NIDS solutions. Examples of NIPS include checkpoint security appliances, https://www.checkpoint.com, and the aforementioned Snort, which is actually an NIPS software package that should be installed on a dual-home or multi-home server. Not only can a NIPS go above and beyond a NIDS by removing or redirecting malicious traffic, it can also redirect or reorganize the attacker to a single computer known as a padded cell, which contains no information of value and has no way out. Like a NIDS or NIPS should sit in line on the network, often in front of the firewall, although it could be placed elsewhere depending on the network segment it protects and the network architecture. Whereas many NIPS solutions have two connections only and are known as perimeter solutions, other NIPS appliances have up to 16 ports, enabling many points of detection on the network. These would be known as network core devices, regardless of the solution you select. As packets pass through the device, they are inspected for possible attacks. These devices need to be accurate and updated often, hopefully automatically, to avoid misidentification of legitimate traffic, or worse, misidentification of attacks. If the NIPS blocks legitimate traffic, it would be known as a false positive, and effectively could deny service to legitimate customers, creating a self-inflicted denial of service of sorts. If the IPS does not have a particular attacker signature in its database and lets that attack through thinking it is legitimate traffic, it is known as a false negative, and also bad for obvious reasons. Many IPS systems can monitor for attack signatures and anomalies. Another type of error that can occur with NIBS and NIPS is a subvision error. This is when the NIDS NIPS can be altered by an attacker to allow for false negatives, ultimately leading to attacks creeping into the network. This can be deadly because the NIDS NIPS can often be the first point of resistance in the network. To protect against this, some devices have the capability to hide or mask their IP address. They might also come with an internal firewall. It is also important to select an IPS solution that has a secure channel for management console interface. One advantage of newer NIPS solutions is that some of them can act as protocol analyzers by reading encrypted traffic and stopping encrypted attacks. In general, the beauty of NIPS compared to host-based IPS HIPS is that it can protect non-computer based network devices such as switches, routers and firewalls. However, the NIPS is considered a single point of failure because it sits in line on the network. Due to this, some organizations opt to install a bypass switch which also enables the NIPS to be taken offline when maintenance needs to be done. A vital NIPS consideration is whether to implement a fail close or fail open policy, in essence deciding what will happen if the NIPS fails. Full fail close menus that all data transfer is stopped, while fail open means that data transfer including potential attacks are passed through. Let's consider an example. Let's say the NIPS was protecting an individual server or router and had a certain level of control over that system. Now let's say that the NIPS failed. In a fail close scenario, it would disconnect the system that it is protecting, stopping all data transfer. This is unacceptable to some organizations that require near 100% uptime. These organizations are willing to accept additional risk and therefore are more receptive to a fail open scenario. However, in this case, if the NIPS fails, it continues to pass traffic to the protected system, which could include possible attacks. Sometimes fail open scenarios are necessary. In these cases, defense in depth is the best strategy. For instance, you might opt to have a firewall filter to the bulk of traffic coming into the network, but have the IPS filter only specific traffic, reducing the chances of IPS failure. This layered approach can offer greater security with less chance of attacks passing through, but often comes with increased cost and administration. So I'm going to leave it here today for this video. If you like listening, please consider like, sharing and subscribing. Thank you.